Feeling thirsty for knowledge? Hackers on the Rocks is the podcast that mixes refreshing conversation with potent cybersecurity insights. Serving up these insights with a twist, we pair a different software vulnerability with a refreshing cocktail recipe each episode. All right, hello world and greetings all around. Our opening segment is called Get Handle Information, and here to bring you today's drink, our guest, the incredible Dr. B Hacking, Dane Brown. Dr. Brown, I am so excited for this drink. Please tell our audience how we're going to break the ice for your podcast.
Oh, right on, right on. One of my favorite drinks in the world. A little tribute to my Jamaican heritage. We've got our signature Jamaican Rum Punch here tonight.
And all right, so I think you've kind of already led with the why. So I guess did you grow up with this drink? Is this like a family recipe? Like go through this.
I mean, after the age of 21 only, of
Oh,
course.
of
Uh,
course. Yeah.
but
Yeah.
it is something that one of the major drinks. Obviously Jamaica is known for its rum, so we've got to have a really good rum punch, and we certainly do. I've actually more recently taken to instead of making it the easy way, making it with all really fresh ingredients and just like a classic cocktail, and I think it's coming out pretty nice.
Yeah, I first of all, I'll just say I'm such a fan of this. I think if you're an active listener of the show, you may even feel my frustration at all of these like lame ass single ingredient drinks, right? Just here's a can of beer, here's a brand of soda, here's a shot of liquor. Like you gave me a one page list of raw. I mean, I feel like I was like, making cane sugar in my kitchen and like, mortar and pestle. And it was a full page of direction. And I guess, yeah, tell us about what we're making or tell us about what we made and how we made it. And yeah, let's run through this whole process.
Yeah, sure. So it says Jamaican rum punch. Important ingredients. It starts with classic Jamaican rum. So the Wray and Nephew overproof Jamaican white rum is the core. It's the base of it. Did you use that too?
No, I had, I say I always try and match my guests, and I should probably figure this out where I don't give guests so much leniency because you were very specific that Ray and Nephew was your brand, and I called around to no less than 2 dozen liquor stores within a 10-mile radius, and no one had it. So I guess I need to be closer to like U.S. naval property to stuff. But out here in Baltimore County, I found me some rum fire, and
Oh, no way.
it is good
Okay,
stuff.
that's funny because I've actually been I've watched a few of the different shows about like rum cocktails in particular, and like that is, I don't know how new it is, but like an up and comer on the scene. And a lot of people are pretty excited about it. I've actually tried to find a bottle, and I haven't found one myself yet. So
I
we're in
will.
a situation, I found my thing, and you found your thing, and we can't meet in the middle.
We are gonna, yeah, we'll have to do a follow-up show in live, in person where we just
Yes.
swap bottles. So, all right, so we start with our overproofed rum, and then kind of run with it from there, man.
Yeah. So then you've got your fresh ingredients, right? Hopefully fresh fruit. Obviously, you can substitute for stuff in a bottle or whatever if you need to. But strawberries, I make an actual strawberry syrup from scratch. As you mentioned before on the page of directions, that was a nice little breakout to show you how to make your strawberry simple syrup that goes along with it. But then yeah, some lime, lemon, orange, right? Fresh squeeze, all of them. Do you want me to talk about proportions, or we just
No, we can put those in the show notes. But I did
if you
find
want to?
a Caribbean store today and picked up some pimento seeds. I could not find those at
Yes,
the grocery store, so we're legit on this. So yeah, I guess
we
we'll
are.
start off with a cheers, my friend.
All right. Yes. Cheers, Evan.
Cheers.
Glad to be here with you. And then, of course, you're garnished. It looks like you garnished with a strawberry. I got a nice little lime wedge going on
I
mine.
can't I can't follow directions all that clearly, so this is what I had. So all right, so while we're drinking, and this is delicious, by the way. Um, this is really, really tasty. Tell us
And
a
then I
little
mentioned it's
bit about,
overproof rum, so you probably don't want to have too many of them.
well, I'll tell you. So for all the listeners, as we record this, it is after 10 p.m. on a weekday, and normally I'm in bed by like 7:30. And Dr. B was like, "All right, I'm going to be running a little bit late." So I'm like, "All right, well, I can't drink the Jamaican rum without him. He's the guest." So Stephen Schaefer was on last week, and I had some leftover for the Paloma. So like There's a lot going on here, but this is delicious. And I guess while we're drinking it, maybe just tell us a little bit about yourself, how you found your way into the research community.
Absolutely. Yeah. So, Dane Brown, I have been, I've wanted to be a hacker since I was a little kid, one of those guys. I taught myself how to program when I was 12 on my TI calculator.
Excellent.
Learned about doing that, learned about assembly even then, that, it was a thing that you could, do in the calculator to have more control and make, have more control over the games that you played on it. So, I went through that, and doing some programming throughout high school. Um, Ended up going to college and majoring in electrical engineering. Because obviously I've done all the programming already. There's no reason to major in computer science. So, only to learn later on in academia. There's more to it, right? And we should never assume that we know everything. But it was actually really good to broaden out to know both the electrical and computer side of things, as well as the coding side of things. And I've been able to marry both pretty well throughout the time that I've been teaching. So I'm a professor over at the Naval Academy now, and I've been there for nearly 15 years. I helped develop their cyber core courses that they give to all the students. So every student at the academy takes two courses in cybersecurity, as well as a major in cybersecurity. So I've developed an architecture course there. I teach the senior electives in reverse engineering and penetration testing, and I also go back and support a bunch of the other intro classes and other classes along the way that they need me for. So it's been a lot of fun.
Yeah, and you and I think, have been friends for a few years, and you've always been very, I guess it's an academic thing, but you're very open with some of the really cool research that you and your folk have done. And yeah, I'm glad you're on our side. That's fantastic what you do. So, all right, let's pause for sponsor, and then we'll dig in, man.
Sounds good.
So, this episode is brought to you by Alexander Cybersecurity Solutions. Alexander Cybersecurity Solutions, or ACS, based in Kansas City, they deliver affordable, top tier managed security services for small to mid sized businesses. Think managed detection, endpoint, and cloud security. Customer focused and compliance ready, ACS has your back. Check them out at alexandercyber.com. All right, so this segment we call the distillery, and Dane is going to take something really scary, and I mean really scary, and distill it down to its simplest terms. So, Dr. Brown, what knowledge are you about to drop on the audience?
Cool. Yeah. So tonight I'm going to do as you asked and talk about one of my favorite topics, which is ROP. We call it return-oriented programming. It's a technique that I've been using probably, I don't know, 10, 11 years now. It's a lot of fun. Some really interesting challenges come that way. And, it's one of the ways that we were able to continue, exploiting the old classic stack buffer overflow. It's an interesting technique to at least know and have in your tool bag. I know there's a lot of tools and things that kind of do things automatically, but I thought it would be a good time to talk about the fundamentals of how and why it works. I think
Yeah,
also, as I get into it, this is probably a good time for me to mention that all the things that I'm going to say tonight are my own personal views and not representing the Navy, the Naval Academy, or the U.S. government.
fair enough. I think a disclaimer is in order. I'll also go forwards and say, if you're listening on Spotify, keep doing that. We love when our play counts can break to like double digit listeners. But Dr. Brown here has made our very first intentional for video episode. So consider checking us out on our brand spanking new YouTube channel at Hackers on the Rocks. So, Dane, you've got some visual props, so I'll let you kind of prep out. But while you're getting all of your tech in order, you mentioned return oriented programming. Can you basically explain a little bit about like what that is and why it's needed in terms of stack based overflows?
Sure. So with a traditional stack-based buffer overflow, right, you would have a buffer on the stack that you can write to, and there wouldn't be any bounds checking on it, right? So that would mean that you can write more than the number of bytes that were originally allocated to that particular object or buffer that's on the stack. The problem with that being that there's usually important stuff following that on the stack. You can overwrite other variables, and even when those variables in the current context of your function are complete, you can overwrite other important pointers. Things like the return pointer that would actually help you get back to the previously running function that called your current function. So if you do that, obviously you are now in control of what instructions happen throughout the program.
Okay, and so we've originally covered buffer overflows, I think, on our very first episode. So our listeners are, of course, encouraged to go back and understand, context of the stack and what Dane is talking about, writing beyond those buffers. Um, and that technique, like let's say we can control that space and make sure that we're not crashing the program because we have everything lined up. But I guess, why would we need return orient? Like why can't I just continue to use the same technique that Aleph One, put forward in the seminal "Smashing the Stack for Fun and Profit" paper? Like,
Smashing the stack for fun and profit. Yes.
yeah. So, like,
Oh, that's good pull out.
why doesn't that work anymore?
Yeah. Well, so in modern systems, right, we've tried to put band-aids on the problem, and so what we would normally do in the LF1 days was what we would overwrite after the return pointer, and obviously tell it where we want to continue executing. Um, we could actually point to code that we had then put onto the stack itself. So either in the original place where I started the overwrite, or maybe somewhere after the return address, there might be space for me to put something known as shellcode, right? Which are bytes that I was writing as part of my string. But if I get an instruction pointer pointing into those bytes, they get interpreted as instructions, right? And the computer actually tries to execute them.
Yep. I'll have you know, this episode is launched in tandem with an episode specifically on shell coding. So
Sweet.
we don't need to revisit particularly all of those pieces, but got it. Okay. So if I'm understanding correctly, then the old way of doing things was I could write somewhat arbitrary lengths, but maybe a little bit of bounds constraint, but I could write my code, and then I can call that. And then now I've basically hijacked the processor and I can control the execution flow. And if I'm hearing correctly, a band-aid solution is to not let that happen. And so you can maybe explain like what is preventing that, and then how that led to ROP being the way to, if we're talking about arms race, like what ROP then overcomes.
Yeah, for sure. So that gets prevented in modern systems with a few protections. The chief one that came out many years ago is called NX, right? A non-executable stack. So the reason that I was able to execute that code that I had written onto the stack was because as a segment of memory, the stack was allowed to be, it had all three permissions: read, write, and execute. And of course, you're not expecting to execute code that's on the stack. Are expecting to execute code that's up in your text segment, which is where the original written code was. So that area of code should be executable, but probably none of the other segments really should be. Obviously, unless you're doing some JIT kind of stuff, but we're not going to get into that here. Uh, so yeah, so after that point, we started removing that execute permissions from the stack, so that even if you did write shellcode directly there, it would be inert and not be able to actually run. So we needed to find a way of executing code that was in other places.
Okay, got it. All right. So the stack is designed for placing variables that would later get read and interpreted. And what was happening was adversaries were putting actual executable code in those sections, and the processor was treating it as code and running it. And that was always wonky. And so as a solution, there's now a special flag that says anything that's in this area, in this region, this memory region, it's not for executable purposes, don't execute it. And so we can't just load shellcode and then call it anymore because it won't execute. And so that brings into ROP. So I guess maybe explain how ROP works. Like, yeah, how
Yeah, certainly.
am I defeating?
Um, and certainly I'm going to show some examples of this coming up, but just in broad strokes, since we can't insert code into the program that's going to be run, because again, we're only able to write onto the stack, maybe the heap, and both of those areas would be non-executable. Maybe you could also write some writable global areas on the data section, but where the code can actually execute is only in the text section, right? Pre-existing code that was compiled into the binary. And so for that being the case, we need to send that return address back up to some existing code. And what we look for then are things called gadgets, right? These are really small snippets of code, right? Maybe just a few instructions at the end of a function that are going to help do one part of what we need to do. So if our exploit needs me to do steps A, B, C, and D, maybe I get step A from one function, B from another function, C from yet another function, and D from one more. And that all together allows me to do some greater, accomplish some kind of greater mission.
Got it. All right. So if I'm hearing that correctly, then I'm not necessarily inserting my own code, which was kind of the old school way of doing things. What I'm doing is I'm scanning all of the potential memory that's available to me and hoping to get lucky by finding the right sequences littered throughout what's kind of already there natively. Is that kind of how this works?
That's right. That's right.
Gotcha.
Making use of pre-existing code and using their own code against them, if you will.
Gotcha. Okay. And now those pieces, like no developer is going to intentionally say like, here's the vulnerability, right? Here's the bad stuff. So like, can you maybe give examples of like what these 2 and 3 and 4 byte segments are trying to do and how we then, I guess, chain them together to form like a coherent piece of shellcode?
Certainly. So your goals may vary from operation to operation. But the most general thing that a hacker might want to do is we call it popping a shell, right? Which is getting yourself an executable, for lack of a better term, a shell, right? So one of the shells that's available inside of that, possibly a Linux system, so that you could actually then execute your own arbitrary commands after that point, rather than just one thing that you're able to do in a moment. All right. So you can use a function. I'll kind of go through this a little later, but a function called execve, which is something that can then execute a new process, and you tell it you want to execute a shell. And then from then on, you can actually feed it directly the operations that you want to perform.
Got it. All right. So I guess we're looking for enough bytes that when assembled in a particular order will run the call to execve, which will then give you shell access to then have interactivity with whatever it is you're trying to do. I guess how do we find those sequences?
Yeah. So and probably this is best done with a tool, right? Because
Okay.
depending on the size of your program, there may be many of these sequences. And so while you could look manually, right, you could go to every function inside of a program and say, hey, what's at the end of this function? Could this be useful to me? What's at the end of this function? Could this be useful to me? And do that a few hundred times until you don't want to do it anymore. Or there's some tools that will do that and find things that kind of have been proven to be useful potentially in the past. And then you can just kind of sift through those and say, oh, here are the ones that might be most helpful for me. And even the one we're going to talk about today is a tool called RopGadget. Will actually generate, if you ask it to, an entire chain that will run execve for you.
Gotcha. And so these tools, right? RopGadget is one probably of many, right? What they're doing, if I'm understanding, is they're 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 basically running through compiled code, right? And that's all static, right? So that could be the program itself.
Right.
On modern systems, it's probably beyond that, right? Because now we're pulling in things from the operating system, from like linked libraries and the other third-party code. And so in totality, this RopGadget tool and or others, um, it's fairly complex, right? It's going through a lot of bytes to find the right bytes that we're looking for to get to that execve. Is that kind of how that works?
That's exactly right.
Okay, got it. Okay, and so um, I guess if I'm thinking through this right, the first thing we need to set this all up is we do need a program that has a classic buffer overflow situation, right? We're still talking about buffer overflows.
Yeah.
And
You need the vulnerability.
all right, so you need the overflow. And then the thing that makes us require ROP is that the stack is not executable. Right? There's some data execution prevention in there.
Yep.
Then we need to analyze like all of the things, right? We're basically
Yeah.
assembling it,
Yeah.
right? Okay, got it. And
Right.
we're finding those bytes and we're finding the addresses of those bytes, correct?
Yes.
Got
Yes.
it.
The address is where those instructions live, which can replace the return pointer at the end of a function. So anytime you're going to return, you're going to now return to one of those addresses, execute those couple instructions, and then return again to somewhere else that's useful.
Can you maybe talk a little bit more about that? Like, because you've now mentioned the word return, and obviously return-oriented programming has the word return in it. Like, what's significant about like what is return and why is that significant?
Yeah, so return is how you, so when you are inside of one program, and this is actually going to make a lot more sense when I'm showing you some code on the screen.
Sure, sure.
When you're inside of one function, um, that was called from another function. We call it the caller. So when you're inside the callee, um, that function has a finite number of instructions, and when you get to the very end of it, um, it has a return instructions that lets the system know, okay, we are finished executing code inside of this callee function. So we want to return to the caller, which means we need the address of where I need to pick up. Right? If like you were in a recipe and you were running, doing step 1, 2, 3, and 4 and you stopped at step 5 because someone rang the doorbell, right? You had to handle that when you're going to come pick up at step 5 when you come back. So our processes need basically the same thing, right? How do I know where to pick up from when I was executing this function beforehand? So that's what our return address is. It tells us to pick up at step 5. But again, if we are running an attack like this, we're going to tell it to actually go to a different step, a step that's actually more in line with what we as the attacker would like to get done.
Got it. Okay, so you're really lining up a bunch of these returns so that a thing happens to prep the environment and then returns to another thing that preps the environment, then another thing, and then by the end you've kind of got all the things kind of where you want them. That's super. Is that right?
Yeah, that's it.
Yeah, that's super sexy. I guess one quick question before we move
Agreed.
to an approach that again is visual in nature to kind of really
Yeah.
lock this in. One of our previous guests talked about another defensive mechanism called ASLR. Does that neuter this ROP approach or not? Or like how does that play in all these things?
Yeah, so it doesn't necessarily. It can be a mitigation against ROP, depending on the places that we return to. We call these gadgets. Okay,
Hmm.
so it depends on where your gadgets are. And so if all you have is ASLR, right, address space layout randomization, which randomizes the location of where different library functions are going to be as your program is running, right? So that's useful if you are using a dynamically linked executable that is going to be calling out to library functions, loading their things in at random places. Um, it would a little bit foil your ability to use one of those library functions. However, the what's in the text section, the actual code that was compiled in many of the cases, is still going to be at static addresses, right? That's not external library code. Um, and then add to that, yes, the library code is going to be at different random addresses, but you can kind of start chaining vulnerabilities here. And if you actually have a way of leaking an address of something that's inside one of those libraries that gives you an idea of an offset into it, you can then figure out where those other um, gadgets within that library would be. So you could calculate it in real time and calculate what the gadget should be.
All right, let
Yeah.
me. I think I just had this aha moment here. So okay, so with ASLR, the addresses are randomized. However, the size of the entire structure is not. And so if the base address is just some random number, and we can
Mhm.
somehow leak some piece of this structure, the offsets are still constant, and now I can either add or subtract to go to the function or the gadget or the byte or bytes that I'm looking. Okay, you're nodding your head. Okay,
Exactly.
that is
Yeah.
super cool. Okay, so in totality, then now we're talking about chaining a lot of exploits, right? So this makes total sense now why some of these exploits in modern era get a lot of press because it's not just, oh, there's an overflow here. It's I had to leak information and then I had to use the information to calculate an offset. and then I am lucky and find all these. But so we're really talking about chaining a lot of really unique technically. It's chaining a lot of exploits together to have one almost desired effect. Is that kind of how?
Right.
Okay. Wow. Okay, that's mind blowing. All right.
It's cool stuff, right? It's
It is
complex,
cool
but
stuff.
you take these concepts together and you end up basically writing one file that does all those steps, right? It's not like you have to do a bunch of work every time it happens. Once you figure all that out once, you write a script and then it happens instantly like magic.
Rock on. All right. Why don't you prep your screen and
Yeah,
like the good podcast host I am, while you're doing that, I'll read a second sponsor announcement.
right on.
Rock on. All right. This portion of Hackers on the Rocks is brought to you by The Hacking Games. The Hacking Games is creating a generation of ethical hackers to make the world safer. With 80% of New York City teenagers having hacked someone by age of 16 and cyber gangs grooming them from gaming platforms, we are on a mission to inspire them to be ethical hackers and make society safer. To find out more, check out www.thehackinggames.com. All right, Dr. Brown, I see
Sure.
a terminal. Tell me what we're about to do here, or I guess just show me
The
and
terminal.
run through it.
Yeah, I
Yeah.
know you said it was going to be visual, and I'm sure everyone was expecting like some nice, cool graphics and everything like that. But no, I do think that the command line. So we're going to have a nice romp through the terminal today.
All right.
All right. So as you can see, or maybe you can't see, I'm going to run through an example problem. This example problem is actually from one of my favorite places, but wouldn't you know, as luck would have it. So it's a competition called Pico CTF. It's a site that's up all the time, literally all the time, right? They leave everything open
Except
year
for
round
yeah.
for people to go to and learn about challenges. I'm a huge fan. I've talked to the folks there. They're fantastic. So I try to advertise them as many times as I can to get young kids into cybersecurity, because I mean, I don't think there's a better learning platform for middle school, high schoolers to see the kinds of challenges you need to get good at, and kind of develop their skill set. But unfortunately, it appears to be down right now. Maybe by the time we finish, it'll be back up so I can show where I got the challenge from that we're working on today. But it was from Pico CTF, which, second advertisement about it, starts at the end of the week. So March 7th, they're going to open up this year's competition. So definitely get any young people into that.
Fair enough. And yeah, we'll put in our show notes Pico CTF. That's a known perennial favorite for sure.
Yeah.
All right. We
So
have the
I am
downloaded
doing.
version. Yep.
Sorry.
No,
Yeah.
go for it, man. I was trying to set you up. I think in the absence of a live Pico CTF environment, it sounds like you've got a local clone.
Yes, I did come prepared. I have learned my lesson many times with demos, so of course have the offline versions that we can do here. So I am doing the ROP-FOO, right? It is a pwn challenge, and pwn is a way that we say effectively binary exploitation, right? The kind of challenge where you're expected to find a vulnerability and find the exploit for it. In many cases, pop a shell, as we mentioned before, so you get the ability to run your own arbitrary commands on the victim system.
All right.
All right, cool. All right, so I think I've already talked about most of the intro stuff about buffer overflows and modern protections. Right, we now have what's known as a write XOR execute policy. I'll put over here, write XOR execute policy in memory, which means, right, and this is our first mitigation, that no segment of memory, right, not the text segment where code is supposed to go, and not the stack or heap or anything, should both be writable and executable. Right? You can see that's what would get us in trouble, right? If an area of memory is writable and executable, then an attacker can write new instructions to it and then ask you to execute those instructions.
Gotcha.
Right? So that is our main protection here.
Okay, so we have one or the other, and that's the NX piece. All right. Do your thing, man. Oh yeah, drink up for sure. Yep. All right.
Cheers. Yeah. We
Yeah.
gotta stay fueled up here. It's a good little hack. All right. So going through the concept here, and why do we need ROP? So I'm going to go ahead and look at this. let's I'll do it in Vim so we can see syntax and everything. It's called vuln, right? So vuln.c is the program that they issue from the beginning, and you can see it is a really short little program.
Okay.
In this program, we do a couple of things, right? And so we actually are given, now you're given source code here, which is the only reason I'm showing the source code, because you could and should solve this all just by looking at the binary itself. But that's the reverse engineer in me. But you can see that we're setting the effective group ID. So that's what GID means here.
Okay.
And that's going to come into play later on as we are trying to get the right privileges to be able to see the flag, right? I have set that up locally so you can kind of still see that happening, right? So we have, set the real, effective, and saved group IDs all to the group ID of whoever owns this executable, right? So if the set GID bit is set on the executable, then if you exploit this program, you will be able to execute things in the context of whatever the group owner of that particular binary was.
Okay.
All right. It then calls this vulnerable function here, which, who would have guessed that it'd be vulnerable, called vuln.
Fair.
Which has a buffer in it, right? So a buffer that is allocated only 16 bytes.
Okay.
Right. And of course, as responsible, people running the program, we will only ever put 16 bytes of data into this buffer, surely. So we get asked, right, how strong is our rob foo? And, it's really simple. It just goes right into it. We have a call to gets, right? And so the gets function is gets the string. And as you're going through this, by the way, and this is for our younger viewers who are maybe less experienced, then you're like, hey, what the heck is gets, right? Always, just kind of open up a different terminal over here and just be very familiar with man pages. I know people Google stuff these days, but all the answers really are in the man pages. So just say man gets, okay? And you will see, hey, this is something to get a string, right? This only takes 2 seconds to do. And you also see kind of like how it's called, right? You see what the arguments are expected and what return value is intended to come back from it, right? There's also a whole part that describes what the function is and tells you what your return value is. This will come into play later on as well. So you get a full description of all the different library calls that you might encounter within an executable. And not only when you're looking at source code, this also works when you're looking at assembly.
Got it. All right. And so, I'm gonna can you actually go pop back into that man page real quick? So
yeah, absolutely. Sorry about that.
For the audience that's trying to follow along a little bit. So if I'm, and maybe correct me if I'm wrong because you're the professor here, but if I'm looking at the code, right, the first part essentially says that we're going to create this block of 16 characters, and that's what we're setting up. And then we're going to ask the user to give us stuff, and that function continues to get stuff, as you can see on the right side of the page, until some special character, that null byte, comes in, new line or end of file. And that's when the getS function stops reading. And so the getS function does not know if what's coming in is less than 16, because all we've done is create a space for 16 at most, or
exactly.
million things in there. And that's the vulnerability. Is that right? Okay, gotcha. All right, thanks.
Nail on the head. Exactly, Evan. Yep.
Cool.
Yep. Right. So yeah, we've only allocated 16 bytes, right? And we are not stopping the user, whoever's doing this, right? This particular function does not stop the user from entering more than that 16 bytes. They can pretty much go until we run out of memory if it need be here. So
there's no input validation here. And so we're trusting that the user knows somehow intrinsically, or will just never set 17 or more characters. Because if they do, then bad stuff happens.
Bad stuff happens, and bad stuff is about to happen.
Let's show me some bad stuff, man.
Okay. Absolutely. Okay. So that is this function here, right? So we know what we're targeting. We're targeting this call to gets with this buffer that should only take 16 bytes. All right. Now, that's all that I think is necessary from the source code side of things. What we want to do is know, okay, well, how many bytes can we write until something bad happens here, right? Yep. And for that, you need to actually see the disassembly, right? So we have the the version that you can execute, right? It's vuln, right? That's the actual program. And so there's a couple things that you want to do every time you have a program that you're going to analyze. At least on Linux, right? I would certainly recommend doing file of it, right? And this tells you, this kind of leads you down the direction. We can actually see this is a 32-bit executable. That tells us some things because calling conventions and whatnot are different for 32-bit versus 64-bit code, right? It is a Linux executable. That's what ELF is telling us. We also see here, as opposed to something I said earlier on, that this is a statically linked executable. All right. And so what statically linked means is that instead of dynamically linked, meaning that it is going to try to pull in at runtime references to those external libraries in C, like printf and scanf, we are going to actually just build the already pre-built assembly code for that into our binary here. This binary now is going to be actually much bigger than if I just, as you saw, this was not a whole lot of code. And it should probably only generate a binary that's about maybe 10 kilobytes. But as we can see, if I do an LL of this vulnerable program here, we can see it's actually 700K, right? Much bigger than something that has just this, two tiny little functions in it.
And so if I'm tracking that, it's back in that source code, the first 5 or 6 lines were include, right? So include these libraries. And because it's statically linked, all of those libraries are actually in this whole program. So the program is self-contained. It doesn't really require anything, but the side effect of that is that it's a really large file. Is that kind of how you, okay, gotcha.
Exactly right. I build this, and certainly I can run it anywhere, right? What we'd say, the lingo here is that it has no dynamic dependencies. If I do an LDD on vuln, since it's statically linked, it's telling me not a dynamic executable, whereas this is a program that would normally tell me, hey, I need to be linking to these dynamic libraries out here in order for this program to run, and here's where these libraries are located. But we don't have any of that because everything's built inside of this really bloated little executable.
Got it. Okay, so we have this like 20 lines of code, vuln.c file, and then it has been compiled into a program. The program is large because it's not just here's the vulnerable function, we're going to print to the screen and just stuff happens, but it's got all of those other pieces into it. And the idea for that is that, again, it's more portable at the expense of file size. So, all right, so we've got this large, massive thing that I'm assuming if we were to look at this in a hex editor, there's a lot of these hex codes. So
yes,
show me what happens next, man.
Yeah, and so the significance of that, just to preview, means there's a lot more code in the binary itself, which means if we need to find something like ROP gadgets, there's a whole lot more functions for us to choose from that might have code that we can use.
Yeah.
Okay? Hopefully it's not a spoiler alert in here, but yeah, that's the important part. Okay. And so the last part that's really important for us to get from file is that this particular binary is not stripped, okay, which means that symbols are included, right? So global variables, I'm going to know the actual names of them. Functions, those names are going to be still in there. And it will make the analysis just a little bit easier than if I was just looking at a huge blob of code in a text segment.
Can you maybe dwell on that for a little bit? So if we're talking about symbols, like what are symbols? Why in a normal situation, not in a Pico contrived example, but like, why wouldn't they just be stripped every time? Or like, how does that work?
So, I mean, honestly, for an end product, you would be stripping symbols generally, right? Because again, symbols are one more thing that makes the binary a little bit larger, and they take up extra space within. Symbols are useful for you as the developer while you're still building the program, debugging it a little bit, and you need those symbols to say, oh yeah, this is that function, right? This is that global variable. But quote unquote, when you're ready to actually ship it, all those problems are worked out, and what you're giving to the end user, you're not really expecting them to debug and need all that information in it. So you want to ship them a tight, efficient executable. So you're not going to generally include that stuff.
Got it. Okay.
You can do that a couple of ways. You can use obj copy -s to kind of strip it out, and you'll get the stripped version, which is going to be a little bit smaller. Obviously, if you're statically linking, you're probably not super concerned about size, but yeah.
Understood. All right. So you've now gone through a couple things, right? So we have an ELF, which makes it Linux. We've got the 32-bit, which you mentioned, it has to deal with calling conventions. It's statically linked and it's not stripped. So we have our base we're feeling good, right? There's a lot of room here. So all right, how do we start the analysis?
All right, so we start the analysis. I'll show a couple of ways. One thing that you might want to do early on is do an object dump, right? So that's dumping the object code. Everyone is going to tell you their own thing here.
Sure.
Certain tools default to showing AT&T syntax for x86 code, which I am not a fan of. I think there's a lot of people who are not a fan of it. Intel syntax is actually just a lot easier to analyze. I think it looks a lot better. So I generally tend to do that. And then we're going to look at that vulnerability, that vulnerable binary. And I'm going to go ahead and pipe that into less. I don't think I have my alias on here, so I'm just going to do standard less.
Okay.
And with that, we can head over to the, there's a lot of areas of code here that we could talk about. Now, obviously, it's statically linked, so there's a lot of functions. You can see I'm just spacebarring and going page by page through this, and we're seeing a lot of different functions.
And we see
We
those
probably
symbols
know that
too, right? We actually see those symbols because the functions are laid out. Got it. Okay.
we're seeing all these symbols, right? We can see the name of these functions that are being called, right? So we probably are looking for a function called main that looks a little bit like this. So one easy thing to do is to hit the / and search for it. So we search for main with the greater than symbol and the colon, and that should bring us right down to where the main function is, right? And we can see from there, if we scroll up a little bit, we see that vulnerable function. So these are the things we just looked at, but it's seeing them here in assembly. And we can see, we're going to look for calls here, and we can see here's that call, that vulnerable call to the gets. So we're doing the get string. Now, from looking at it, we know, hey, we were supposed to only put 16 bytes in that. But I don't see the number 16 anywhere here, until we're adding that to the stack pointer, which is not actually related. We right here are loading the address of where we're going to load that buffer. And we can see that this is 18, hex 18. So that translates to 24 bytes above this is what's known as our base pointer, EBP. Okay. So we have 24 bytes that we can write until we hit the base pointer. Obviously, if we only type in 16, it's not going to be any problems. We're never going to get to that base pointer. But by the time we type in 24 bytes, we have 4 bytes of the base pointer itself. So if we do 28 bytes, we've now overwritten that base pointer. And the way that our stack works is directly after this base pointer is that return pointer that we're targeting. So I can tell just from this, right, hex 18, that's being 24 plus 4 bytes for the base pointer, that at 28 bytes, we start overriding the return pointer, right? So we want to figure out what 4-byte address would we like to put there.
Okay. So the idea is to fill 24 bytes of arbitrary, it doesn't matter, and then at that 25th byte, is that right? Just put an address that helps you.
At the 28th byte, right? Because the 24th, 25th, 6th, 7th, 8th are going to be for the where the base pointer is. But yeah, at 28, we start overriding the return pointer. So those next 4 bytes are the address of where I'm going to return to, right? What step in my recipe am I coming back to after I've answered the door?
Gotcha. It's rum, right? That's the step.
It's rum?
It's rum.
Yes, it's definitely add the rum, for sure.
Gotcha. Okay, all right. Okay, so we understand how much flexibility we have from looking at the static code, and now we just have to figure out all those gadgets, right? So there's a lot of code here. So how do we sift through it, and how do we know what we're looking for?
Yeah, for sure. Great question. All right, so now is the time when we want to make that decision. We need to find these gadgets. Before we do, though, I want to very quickly, if you'll indulge me, tell you what it is that we're trying to do with these gadgets. I know you said you're already doing a thing on shellcode, but I've actually kind of written some stuff up to kind of show us what it is we're trying to do shellcode wise here, right? So exec.ve, I have a couple of versions in here. So if I'll do vim of exec, and I have like the standard version. So again, as simple as possible programs here. Here is execve. What it takes to do it, right? So we include the Unix standard library. That's where execve is. How do I know that? Because I looked at the man page, right? Man to section 2 execve, and it tells us exactly this. Hey, we need to include the Unix standard library, and here's how you call execve. I usually copy and paste this every time I'm going to do it, just so I know, hey, here's what all, or any function, here's what all the arguments are going to be, here's what it's going to return, right? Get all the description here. So execve, in order to call a function, generally wants that path name to it, right? So we're going to make an argument buffer here. And the argument that certainly we're interested in is, bin sh, right? That is the path to the shell executable.
Yep.
Okay. Then the second argument, right? We give it the argv, the whole vector itself, which is kind of all of this. And then we give it the environment as the third argument here. That's this env part. Of course, that can be null. And in many cases is, unless you want to give it an entire environment at that point. Okay, so what does that do for us? All right, I have made a little makefile here to build all the things that we need to build. So that makes the things a little bit easier to follow. It will show you, of course, how it's building. So if I'm going to make this standard, right, we can do a little gcc command for it and create this this exec version.
Yep.
Right? I can do file exec and show you all the things that we did before, but mainly running this, again, as simple a program as possible, 2 instructions in there. This gives us a shell, right? Here's a bin sh shell that I've ran inside of my own directory here with full permissions. I can still see that I am my own user, right? I'm still Dr. B hacking, but I have now written the code that that pops a shell on my system.
Yep.
Okay. I'll pop out of that real quick here. Do you have any questions at that point?
I don't think so. Not yet.
Okay, cool. Now, that version is still a little bit more complex than we need. So I've made another version of it, right? Exec null, right? Again, when I'm writing shellcode, I want to put the minimum amount of code in there as possible, right? So rather than making this whole buffer and having, this whole argument array, it actually is possible to do this with nulls for both the second and third arguments. You're going to see how that makes shellcode a little bit easier. So all I need to do is find this bin sh argument for the first argument and call execve as well. Now this works the exact same way. So I'm going to make exec null. You can see just warnings, doesn't matter. It's going to tell me that wasn't really a good idea. But when all said and done, I do the execution and it gives me the exact same thing, right? Yep. I've been able to pop a shell successfully. Okay, good. Out of that, I'm going to delete all those things, could do a make clean here and be able to move on. Okay. So that's the desire. Now, obviously doing that in C is no problem. But when I have a buffer overflow, I need to put actual instructions, right, at the assembly level, right? I unfortunately can't do a buffer overflow and write new C instructions in, right? Everything's already been built. It's already down to machine code. So with that being the case, I need to find out how to do this at the assembly level.
Okay.
All right. And I'll show you kind of what this should look like here. So here is some shellcode that basically also will do execve for us. So vim, I think this was shellcode ideal, right? So ideal.asm. So I wrote this up for us. And this very simply, now there's multiple ways to do this. Everything's shown up on the screen here. So that's good. Nice and convenient. So we have in the data section, right, just this shell, basically a variable, all right, that I've nulled out, right? So that's kind of all zeros to start. Will automatically have my null terminator for me, which is good. And I want to do basically the same things. I'd like to build the string bin sh, okay? And I'm going to put those at my shell location here, right? And so one way of doing that, now there are multiple ways of doing this. One way of doing that is to just kind of move these into that location. So I get the address of shell, right? And I can move the bytes that correspond to the ASCII characters for the / b, I, and n, which is this. And those are in something known as Little Endian format.
Okay.
Don't know if you want me to get into that or not, but we have to reverse the order of all these bytes because it's represented differently in memory than it is in the registers.
Gotcha. So you're saying that 2F represents a slash, and then
Exactly.
yeah, okay, gotcha. And then
2F is the slash,
yep, we're working
62
our way
is the B.
backwards. Yep.
Right. Great. So with that, and then we need to do it with both strings. Now I have to do this 4 bytes at a time because again, we're in a 32-bit system, right? And so our registers hold 4 bytes. So I can put 4 bytes in the register and put them into memory in this way. And then I just want to make sure at the end of it that I have a null terminator after those 8 bytes have been written. So now I have a string, right, that's going to replace these bytes at this location inside of my data section.
Yep.
All right. And we know that's going to be my first argument to execve. Right. So after that, I just need to get basically the pointer to that by my calling conventions for 32-bit here in EBX.
Yep.
Okay. I load that. I then get my other arguments, right? ECX needs to be that null. Remember, I showed you null.
Yep.
I can do this with null without pointing to a whole array anymore. And then I get my syscall number out in EAX. So I have to find the syscall number for execve. And the way we call a system call, all of them, right, regardless if it's execve, write, read, anything else, is with this command here, int hex80. Okay, so that's an interrupt, and this number actually performs a system call.
Yep.
Okay. One thing that's actually kind of important for us to find, I already showed you the man page for showing what execve is, but where in the world did this system call number come from? Yeah, one more thing that we want.
Are we
yeah.
to a man page?
Yeah,
Please.
I was teeing myself up to answer that one.
All right, so we're loading 11 onto the stack, then we're issuing an interrupt, and
exactly.
Show me where the syscall is, man.
yeah. So we load 11 in as a syscall number, but we need to know what that is. So we want to find that location, which is less. This is actually in user include. This architecture x86. It's under assembly, and it is our unit standard H. No. Yeah, 64. You understand? Oh, sorry, 32. Right? Didn't I say it was 32-bit? So we want to go to Unit Standard Library 32, and there it is. Here is our syscall numbers for 32-bit binaries. Right? So we can see exit is 1, fork is 2, and then right down here, number 11 is execve. So whenever we want to do execve, we need to load that system call number of 11 into EAX before we execute the interrupt. All right. That is our goal here.
Okay. I think I'm good. So now we need to basically find the equivalent bytes in somewhere within that large statically linked non-stripped file. That's kind of where we're at?
That is correct.
All right.
That's absolutely correct.
Okay.
With one small caveat here, which is if I was to actually if I took this is what I want my shellcode to kind of do, but this isn't what I want my shellcode to be, right? There's a little caveat here, which is I'm going to go ahead and build this, make shellcode.
Ideal, right?
Well, that was ideal, but this is the null version here.
Okay.
This isn't one we kind of talked about yet, but when I do this, right? I'm going to actually make it as if I was creating just shellcode. It's not going to be a full ELF binary, right, that I can execute on its own. This is just going to be those instructions that I would have overwritten the, after the return address and had it point back to on the stack if I could execute things on the stack. All right. So I can look at those instructions here. Actually, I'm going to start using my favorite tool ever because I give myself a reminder to, which is Radar2. That's how I do all my hex editing and do this analysis. But I can tell it that I'm going to look at a 32-bit program here with this null shellcode. Now, this shellcode is really tiny. I should have proven that to you first before I came in to do this. So I'll do that real quickly here. But if I do an LL of SC null, you can see this is just 60 bytes, right? Yeah. This is a small thing here, but there is a problem with it, right? Which is, if I look at this, I'll look at it in the visual mode and just look at the code. This is, exactly the code that I have over here, right? Obviously the symbols aren't there, right? We don't have variable names and everything, but everything else is exactly what I've written pretty much. And
Okay.
this is what the ROP gadget is going to give us, which is why I wrote it like this. But there's one problem here, which is if I tried to use this as shellcode, right? I could write these bytes onto the stack, but remember we use that gets function, gets, gets. Now, even though this code would, if it was all written in memory, pop a shell for us, we do have a problem.
Hmm.
Do you kind of see the problem here?
I mean, it looks like it's longer than the 24 bytes that we get, right?
Yeah, it's longer than those bytes, but we kind of wanted something longer than those bytes so we could overwrite the return address.
Okay.
The problem is gets is expecting a string, and a string in C is terminated with a null byte.
And there's a
And
bunch
so
of them
all
right
these
there.
zeros,
Line.
yeah, and there's a bunch of zeros here, right? We have not written really good shellcode here because a lot of these instructions have zeros in them, which would actually end my shellcode, and it wouldn't all get written in. So I would have to actually have done more work here to write shellcode that doesn't have nulls. It's not tremendously difficult, but it wouldn't help us anyway because we can't execute this code, right? We have to go to ROP. But this is the other advantage of ROP is I can and will use code that's exactly like this because it doesn't matter if ROP gadgets are pointing to code that has nulls in them because those already exist in memory, and I'm not going to have a string terminated as I'm trying to write it in.
All right. I'm with you so far. Okay.
Beautiful. Okay. All right. So doing this, I want to pick those gadgets, right? Is exactly what you mentioned. So we're going to look at our function here called ROP gadget. Okay. So ROP gadget is what does this for us. And I'm not going to run it. I was going to kind of run it in the Pico CTF shell for us, but I've already done it. And so we can look at what it gives us, right? I'll just go straight to the chain. So when you run ROP gadget on the binary, it shows you all the addresses, right, that point to code that end in something that will, return or go to somewhere else, right? Sometimes they're jump statements, but a lot of times they are actual return statements. And so many times before a return, we actually end up popping data like off the stack and putting them in registers, which is exactly what I need. I need EAX, EBX, ECX. I need them all populated with specific instructions before I do my int 80 syscall. Okay. So what I would need to do is kind of search through all these. And like we mentioned, it's a statically linked program, which means there are so many of these functions for us to choose from here, right? So we could spend a long time going through this, which I'm not going to do. What I'm going to do is I'm going to hit Control G because I did give it also the option to generate a ROP chain for me that will execute execve as I need to do. So I'm going to head down to the end of the file, and sure enough, it basically gives me the code and explains what that code is, which gadgets we needed to do that. So it tells me ROP chain generation, and the things I need for that are a write what where gadget.
Okay.
So write what where gadget means that I have the ability to write something to basically an arbitrary location in memory, right? I also need to basically set up what my syscall is going to be, right? The number for it, and then put my arguments together. So these are gadgets that will put things into EBX, ECX, and EDX, right? As we knew we needed to do. And then obviously doing the syscall itself. So needed to find an int 80 somewhere in there. And once we have those basic requirements met, it actually gives a little Python script together here that will chain all of those addresses that get those things done. And the reason I'm not going to go into depth into this is that it probably looks kind of similar to the shellcode I just showed you, right? So I made shellcode that basically did what these gadgets are doing. And I did a couple versions of it that get more efficient, but I can kind of skip to the end version of it if you'd like.
Yeah, I mean, I think this is pretty clear. So this tool called ROP gadget actually speaks those ROP gadgets, identifies them, sequences them, and then can actually push out a Python script that has all of the addresses of those gadgets ready to go. Pretty neat stuff.
Yeah. Okay. So good. So now that we have that, we have that chain. So we have one that's generated. So I can actually make one that, so let me see, let's see, from the ROP chain that we've generated here.
Mm-hmm.
And so you can see I've made a kind of a version of the shellcode that does that. If I do an LL of that shellcode, all right, we can see there's quite a bit to this because I've made now a full elf, right? This is a full elf that will actually perform perform that function, right? Shellcode that should get me a shell in the same way. So now in assembly, right, those instructions will do that for me, right? From what ROP gadget generated. I went one step further and did a slightly different version. I'll take 1 second and show you them side by side.
Okay.
For one particular reason, right? So the shellcode that they generated came from SE generated. Oh, I need to tell it that I want to view it. So I'm going to vim shellcode generated, ASM, and the shellcode final, right? My final version.
Yep.
And I'll put those together vertically in Vim, so they'll be side by side, right?
Okay.
So my final version that I did is on the right hand side, and on the left hand side is something similar to what I just showed you. So what's really interesting about a tool like RobGadget, it's a great tool, right? It makes this a little bit easier for us, but it does things a little bit like a compiler would, right? It's a machine that's generating code. And in the same way, if you write assembly, you're going to write something that's very different from what a compiler would generate. It's not necessarily going to do things really efficiently. It's just going to give you something that works. And that's kind of what we see here, right? And so if we blindly take this, it will work, but you'll kind of notice there's a couple of things that are not super duper efficient over here. Like, for instance, getting EAX equals 11, I set EAX to 0, and then I incremented it 11 times, right?
Yep.
This is all well and good if you have enough space to do kind of all of that, right? But if we look on the other side here, there are other gadgets. If you kind of go through that list, again, there were a ton of them since we have a static binary, and you can see how much shorter my code is on this other side. I actually found a gadget that just directly puts 11 into EAX, right?
Yep.
Now, ROP gadget is not going to spend the extra time looking for that, but you might find things that do things like that, right? So I found another couple of efficiencies, but that kind of gets the general idea of what's going on. And if we look at the generated version here, that shell code, right? So if I make the SC final version, my final shellcode version, we should now see the shellcode that I get from this, right? Well, actually, that's only a little bit less.
A little bit smaller. 4 bytes.
What's that?
Well,
it wasn't that. I think I'm looking at the. I'm more interested in the object code. SC final.o. Yeah. Right. And then the SC generated.o. Right, where you can see a little bit more of the savings. And if you had actually built these in the exact same way as like shellcode here, the difference would even be more stark. It's like 50% savings by just finding something that's a little bit more efficient. So if you had a limited buffer that you could write, you might want to spend a little bit more time searching for other things. Okay, so that's what I kind of wanted to show there. Now, I think that's the pretty total explanation of what ROP is, how I found the gadgets, how I generated my exploit. And so you can see I've actually put that into, there's a Python program here, solve.py, right? And all this is basically a copy paste of that ROP chain that we saw.
Yep.
Of course, but using my, I did one that used my more efficient version as well. Oh yeah, so I did one using my more efficient version, and we can see the code for that underneath. But it starts with everything that we mentioned here. A garbage 24 bytes at the beginning, another garbage 4 bytes writing over our base pointer, and then the rest of our exploit being these addresses we need to go back to. All right, and that gives us our exploit code. So that is actually what I was looking at here. So if I look at my exploit code, those are the differences here. I meant to do this, right? LL of my exploits. these are the two versions, right?
Significant. Yeah.
What we get from ROP Gadget, the exploit code generated is 176 bytes, and what we get from doing a little bit more efficiency is 116 bytes, right? So the original thing is 50% more code, a bigger binary than what we have, right? And maybe easier to find, all those things. So we've got that built, and so what we can do is we can send that into the binary.
Okay.
I can show you what that looks like, by the way, as well. So it's just exploit dot final.
Yep.
And this is what it looks like. That's all the address is, my initial buffer. So sending it in, we can just use like cat. Now, where I have this is in my challenge folder. So I'm going to cd into the challenge folder. And so this is something that just has it, right? If we look in here, our actual challenge is to get this flag. And as we mentioned earlier on, here's flag.txt, but it's owned by another user, okay, and a different group.
Yep.
And only they have read and privileges. In fact, the group only has read privileges and not write privileges. And as we saw, this binary, vuln, was a set group ID binary. So the RWS here means if you execute it, anyone can execute this. That's the other over here. But anyone who does execute it will get the permissions of the privileges of the group, which is CTF in this case. All right. So if I can exploit this, this process here that has set GID bit set, I can now get myself permissions to read this flag, which obviously doesn't work right now. I'm going to do that again. And I'm going to try to cat the flag.txt. I've got permission denied.
Sure.
I'm not that user. I'm not that group.
Okay.
Okay. But now I'm going to go ahead and run that process, right? I'm going to run the vuln, but I want to give it my input. The way I'm going to do that is by catting it in. I'm going to cat that exploit, the final exploit from before. And I'm going to do a dash here. You know what this dash means?
Do tell our listeners.
All right. So this dash here will keep standard in open and allow me to keep typing from the terminal. So what I'm going to do is I'm going to pop a shell, and I don't want that shell to just immediately close on me. So if I keep standard in open from what I'm sending in, I'm going to be able to keep giving it input from the terminal with me typing into the keyboard.
Got it. Right? All right. So then just overly simplifying before we hit that enter key, if I got all these steps right, vulnerable .vuln is the vulnerable program. We've looked at that, and it allows the user to enter in as much as it wants, but it will terminate once it hits a delimiting 0. And so we then crafted a really large string, right? Not 16 or less as was designed, but something a little bit larger, 700 bytes. But none of them have that special termination character until the very end. And so the vulnerable function is going to actually pull in all those things. And then as it starts processing them, those are addresses of all of those gadgets that we need in the right order to align the stack such that we're getting ready to call execve on bin shell, and all of those things are in the right registers at the right time.
100%.
Show me some
Hopefully
magic.
The stars align.
Yeah, exploits are amazing. Let's pop something. Let's go.
Hoping the stars align first here, right? And so with all that said, right, I don't know how long we've been explaining this. Maybe
do we have a drum roll? So. Yeah.
A drum roll, please, right? Everything comes down to just hitting enter here, and hopefully, I don't screw up this demo. But there we go. We can see the string that comes up. How strong is your foo? And it hasn't finished here. I'm going to hit enter, but now it looks like potentially I still have access to this. I'm going to go ahead and type ls, and it looks like it's returning things like from a shell. And if I do ID now, before I delay showing the flag, but if I use the ID command, I can actually see that yes, my user ID is still Dr. B hacking, but my group ID has been upgraded to the CTF user, and so I have whatever permissions someone in that group has inside the system. With which I'm going to try to cat flag.txt, and there we go.
Look at that. That is, I appreciate the flag as well. That is magic. I can see why you are I can see why you're Dr. B hacking. I love it.
I love it. How can you have more fun than this?
So no, you can't. This is why we do what we do. So let's pause it here. I think this was super fascinating. I mean, very crystal clear as to how these things work, the impact, the danger. how some of these, this arms race again between, oh, it's an executable stack. Oh no, it's not. Oh, that doesn't matter. I guess in terms of our the way we always close out our show is with a last call, and so I think we're really good on everything you've shown, right? So I think ROP makes a ton of sense to me, and so hopefully it now makes sense to our listeners who are much smarter than I am. Where can people go to find out more about you, your work, your projects, your research, anything you mentioned today?
Sure, yeah, yeah. I'm always around. I mean, right now, I mainly Twitter, right? I'm Dr. B hacking on Twitter.
Yeah.
I guess it's X now.
Cool.
But yeah, I've been known to post some stuff there every now and then. Um, I plan to branch out into some more social media stuff. I'm going to make a LinkedIn one of these days, I swear. But yeah, we'll see.
Fair enough. Well, if you're one of our listeners, you have every right to go get Dane Brown for LinkedIn before he gets it. And
Don't you dare!
wait, what?
There's like 1,000 other Dane Browns, so
I don't know.
I'll be one
There's
in the sea.
only one Dr. B hacking. I don't
Only
know.
one Dr. B hacking.
Fair
Exactly.
enough.
I'm also coaching the U.S. Cyber Games. So
Yeah,
proud of
tell us about that. What is that?
yeah. So the U.S. Cyber Games is a group of young, like really talented hackers. Right. These guys are special. It's something we started up about 4 years ago. Not long before we met.
Mhm.
And we recruit, college age, some a little after, some a little bit before college age, hackers from around the country, and have them compete internationally, right, representing the red, white, and blue. And it's been awesome, right? I think it's something that challenges them, puts them in a community of like-minded people to grow faster than they hopefully would have alone, and set them up for really great career opportunities, which we've already seen happening. So, yeah, really glad to be a part of it, and always recruiting, looking for the next generation of awesome talent that's going to lead our country forward.
Yeah, well, look, I think spectacular talent clumps together spectacularly. So I think the men and women that are part of that effort are just inherently the next generation of magic. So I'm
Yeah,
really glad that you're active in that. And yeah, look, Dane, thank you. I really appreciate you taking time out of your evening now to distill out Rob gadgets. And yeah, thanks for being a guest. This was fantastic.
likewise, Evan. Appreciate you, man.
Yeah, cheers.
Fun. Cheers.